This chapter introduces the idea of limits with a really practical example. It's one that you'll see a lot if you take a physics class, and that's with the law or the motion of a falling body. So let's go ahead and look at the same kind of an idea, but we'll look at it with just a different equation so that you can see it worked out, but just not with the same kind of an example. So we'll pick. How about we'll just take an exponential equation. So let's say that our equation in this case is going to be y equals 2 to the power of x. So your average velocity is just going to be your function at some time 1 and subtract that function at time not time 0. So really this is just the change. In this case it'd be position because we're talking about velocities. So your change in position over your change in time. So you think about something like miles per hour, your miles over hours. But doesn't have to be like that. That's just, doesn't have to be those units, but kind of give you an idea of what we're doing when we talk velocity. So let's see this velocity equation on an average velocity plugged into our the equation that we have, 2 to the power of x. So let's take it, let's go from 0 to 2. So let's say we want to find the average velocity from 0 to 2. Well, we got our v average. That's going to be our function at x equals 2 minus our function at x equals 0 over 2 minus 0. Again, just to say you don't really have to pick 0 for t naught. It just kind of, I picked that because the math will work out a little bit easier like that. So f of 2, well, our function is 2 to the x, so we've got 2 to the power of 2 minus 2 to the power of 0. 2 minus 0, that one we'll just do the math real quick. Anything minus 0 is just 2. All right, so let's keep going. 2 to the 2 is 4. Anything to the 0 power is 1 over 2. 4 minus 1. That gives us 3. Now you'll notice here, this is also the same way that you find slope, right? This is your y values, so your change in y over change in x, or rise over run, or however you've probably heard it in some other courses. So let's see what this looks like on a graph. We'll pull up our graph here. Y equals 2 to the power of x. All right, there we go. And then let's put our other equation here. We'll say y equals 3x over 2. All right, and then we're going to have to, let's move this up. There we go. So that let's take a look. There it is. All right. So you'll notice here that this is our starting time, and we intersect the graph. Here's our motion graph right here. And then our ending time is 2. And you'll notice that our line intersects our curve. There's our curve at that as well. So anytime that you take an average velocity, you'll see it is going to intersect at the 2 points. And pretty much will just be a straight line connecting those two. So let's move this in a little bit. Let's say we want to take it instead of 0 to 2. Let's say we want to go from 0 to 1. Okay, so we had 3 halves before. So let's do it. V average equals, so we're going to have our function at 1 minus the function at 0 all over 1 minus 0. Okay, move that up a little. All right, so our equation is y equals 2x. So we're going to have 2 to the power of 1 minus 2 to the power of 0 over 1 minus 0, which is 1. So 2 to the power of 1, that's 2, minus 2 to the power of 0, which is 1, over 1. All right, 2 minus 1 is 1. So now, in this case, we have a slope of 1. I guess we need a box around the other one. Let's box around that one. All right, so let's take a look on our graph here. We'll say y, oops, there we go, y equals, so x, 1 to the x is just x. And let's go ahead and move our graph up a little bit there. Now you'll see the line here was the gray one is our first slope right there. And now we have the same kind of an idea. Our line intersects, here's 1. So our line intersects at t equals 1 and t equals 0. So there's our green line right there. And you'll notice that the average velocity is changing the shorter and shorter that it gets. So let's take this idea. Let's say, well, what would happen if let's say we want to find the instantaneous velocity at time 0, at t equals 0. So if we zoomed in right here at time equals 0, what is the instantaneous velocity here? Let's get rid of these real fast so we can see there. All right. So what would it be if because we started off with 2, then we went to 1. So let's see. Now there's you can do this one of two ways. You can do it by hand if you really wanted to, but let's take a look at it in Excel, because that's Excel's gonna save you a lot of time in this case. So I'll arrange this so you can kind of see. All right, let's call this one. We'll call this, I guess we should label it T naught. And then I'm going to say, well, T naught, we'll just say 0, so we'll say T1. Okay, so T naught's going to be 0 all the time. And let's say we'll start from 0 to 1, but let's then, so in Excel, if you want to make an equation, you hit the equal sign. I'm just going to take whatever is previous, and I'm going to divide it. Whoops. I'm going to question it by 2. No, I'm going to divide it by 2. There we go. And so let's do this a few times. All right. So this is going to say, okay, well, this is from 0 to 1, 0 to a half, 0 to a quarter, 0 to an eighth, to a 16th, to a 32nd, so on and so on and so on. So by the time we get down here, it's a pretty small change. So now we'll come over here. Let's plug in our equation. So I need a couple parentheses here. So we're going to do our function at t1. So this is going to be 2 to the power of this one. Subtract t naught. So, oops. No. Oops. Okay. Lots of errors. All right. So subtract 2 to the power of that. Now here's a little Excel trick. Let's say that you don't want this to change at all. You put a little $ in front of the A and in front of the 2, and that just means that it's only going to reference just this. It's not going to move down when I move that down. So okay, so I've got 2 to the 1 minus 2 to the 0. All right, so that's pretty good. Then I want to divide it by T1. Let's put parentheses. T1 minus T naught, and we're going to need our little $signs. All right, I think this should work. Cross your fingers. Voila. Okay, good. And we can kind of verify that our program is working correct because we calculated that by hand, and we got an average velocity from 0 to 1 of 1. So let's just drag these down. Here we go. Now, you can see this slope really once you hit like down here, you notice that it's not really changing very much. You've got pretty much 0.693, you know, it looks like it kind of lands on 0.6932. And you could do this, I mean, that's the great thing about computers. You could do this all the way down if you wanted to. Now, we're going to figure out how you would solve this, by kind of by hand. So I solved it out by hand, and I know that the derivative, which would be that instantaneous velocity, is going to be 0.69314. So it would just get closer and closer and closer to that. But instead of actually doing it like that, we're going to use this idea of instantaneous velocities as with using limits. So what the limit would say is, what would happen if you took this difference right here as the difference approaches zero? As in, eventually, these numbers are going to be so small that it's not going to make any sort of a difference. Well, I mean, it would depend on if you really wanted to take your numbers way out far, but in all practicality, it's not going to make really any significant difference. And so if you took the limit as this delta, as the change in time approached zero, that's going to approach some value. And whatever value that is, that's going to be your instantaneous velocity. So let's take this from this last one. So 6932. So let's come over to our graph, and we'll say, all right, so y equals 0.6932 times x, and then plus 1. So if you look right here, you should notice, and we can zoom in really close, that this is going to be our instantaneous velocity, the slope of this line, right on the single point of t equals 0. So let me zoom out so we can see the 0. There we go. A little bit better picture. So that's going to be our instantaneous velocity, is what's going to be the limit as your change in time approaches 0. And so that's kind of the idea, the basic idea of where we would use these limits, or how these limits are used in calculus. So in the next couple chapters, we're going to actually dive a little bit more into limits, but this is just a good example to get us used to the idea of what exactly it is that we're doing.